Okay, so Andrew Woods, he's the BP professor at Cambridge University. He's also professorial fellow of St. John's College. His research interests are in a wide range of fluid flow processes, including, and really, I think, really well known for geophysical flows. But he's interested in things as widely different as exploding volcanoes and multi-phase flows in petroleum engineering. Among many other honors, he has been elected to the Fellow of the Royal Society, or he is a Fellow of the Royal Society. And he will talk to us today about the fluid mechanics of deep sea mining. So thank you, Andrew.
Great. Well, thank you very much. So first of all, just a big thank you for inviting me to give this seminar. And I think this new journal is very exciting, looking at putting applications of fluid mechanics together to complement JFM. And I think in this talk, I'm going to talk about an application of fluid mechanics in understanding sediment dispersal in deep sea mining, which I hope is sort of appropriate for the flow journal. And so the context behind this work is really that with the energy transition, there's a huge need for a lot of natural resources such as manganese, nickel, copper, cobalt for electric vehicles, batteries, and there's a huge amount of new extraction going to occur for this. And one of the big areas where there's a lot of interest is on the bottom of the Pacific Ocean, where there's polymetallic nodules, and I think you can see these on this lower picture here. These are about tennis ball size accretions that form basically with very high concentrations of these minerals. And so there's a big industry developing to see if they can be extracted to provide the raw materials for the energy transition. But of course, there's a lot of interest in the potential environmental impact of this. And the zone in the Pacific Ocean is shown here where these nodules are. So it's a very big area, about 1 million kilometers squared. And you know, there's a lot of ecosystems on the seafloor at depth in the Pacific Ocean there, and they're very highly sensitive to disturbances. So there's a lot of interest in understanding where the sediment that may be suspended from the seabed will go, and how it will impact these ecosystems. So that's the sort of context behind this. And just to give you a picture of what's a cartoon of the idea, there'd be a sort of drill ship or a drill rig at the surface, and there's 3 or 4 kilometers of water, and on the seabed there are these nodules and a series of tractors, and these are some of the machines that go down to the seafloor, and will go along and scoop up the nodules, and then they'll be brought up to the surface onto either a drill platform or onto a transport ship along a riser. And as this is processed, there may be some tailings, some very fine particles that are produced, so that the drill ship just keeps the value, or the transport ship keeps the valuable materials, and they'll be discharged back into the ocean. And I guess the interest today is, where do all these particles go that if you put them back into the ocean? And so that's what we'll be looking at. There's also a whole series of interesting fluid mechanics about where the sediment that's or suspended by the tractor itself goes, but that tends to be somewhat more localized than the transport of this big plume we'll be looking at today. And just for reference, you know, the ocean currents have speeds of centimeters, up to meters a second. These plumes we'll see have speeds of millimeters to tens of centimeters a second, and the particles themselves, there's a whole range of sizes, but they may be hundreds of microns typically, and so they'll have full speeds of millimeters, maybe up to tens of centimeters a second through the water column. Well, to understand some of these problems, we can first look at the case where the ocean is regarded as being static. And this is an experiment where we have a density gradient through a tank of water in the lab. So it's fresh water at the top, becoming salty at the bottom. And we're going to supply a mixture of fresh water and particles at the top. And the point of this experiment is really to try and understand the role of stratification. This just shows the density through the ocean, which is a combination of the salinity gradient and the temperature gradient. But the result of that is that the density of the water in the water column typically increases with depth. And so if we release our particles here, let's just watch this movie run, the particles come in, and as they settle through the water column, a turbulent plume develops in the top part of the tank here. That entrains the fresh water, the mixture becomes, and the mixture is finding itself moving through progressively more salty and denser water. So at some point, the mixture of the dense particles plus this fresh water has the same density as the water here, and the mixture intrudes in the water at this level. And after it's intruded, it starts spreading out. And then the particles, because they're dense, they start separating from the water. So there's no longer moving with the water, but they start separating, and they sink down and form this sort of sedimenting cylinder of particles that sinks to the base of the tank. And there's some very interesting small-scale convective structures that develop as well. So that's what happens in an environment that's static. And one of the questions about this is, where do the particles go? What's the depth of this intrusion? And particularly, where is the water that was carried down and produced when this slurry of particles and water came off the drill ship? Where does all that water go? Because that may have some dissolved minerals in it, and there may be things that are you wouldn't really want to see in the water column, and you want them well dispersed. So to do this, we can draw from the literature on turbulent plumes. And in a turbulent plume, in a simple plume where we have a stratified solution and we inject salt water downwards, the salt water mixes with fresh water and the density gradually changes. So here's a picture showing density and depth. So we put in some salt water. This is the background density. The salt water comes down, it entrains the ambient fluid, and the density of the water in the plume gradually approaches the ambient. There's some momentum, so the flow overshoots a bit, and then it intrudes at a particular height. And by dimensional analysis, we can predict that height. Morton Taylor Turner did this 60 years ago, and it depends on the stratification of the water column, the density gradient in the water column, and it also depends on the buoyancy flux. So this is the flux of reduced gravity. So G prime is the effective gravitational acceleration, and Q is the volume flux. And by dimensional analysis, we see that the height just depends on the buoyancy flux and the stratification. And the buoyancy flux is the key variable here, because that's really expressing conservation of salinity or negative salinity in this plume. And in the case of the particle plume, it's just expressing conservation of particles. Well, in a particle plume, in contrast to the saltwater plume, when the fluid reaches this depth and it intrudes, the particles then fall out. And so the remaining fluid finds itself a bit less dense. So it rises up and intrudes higher up in the water column. And so with a simple argument, we can find this height relative to this, and it ends up being about 5/8 of this depth here. So that the red fluid, which has come with the particles, intrudes at a depth of about 5/8 of the blue fluid. And there's a simple analytical approach to understand that. And experimental data agree very well. So the maximum depth is the initial depth it goes to. The neutral cloud in blue maps very well, and then this particle cloud, or the cloud of fresh water with the particles, is actually quite a bit shallower. And if we're trying to look at the environmental impact of where that water goes, that's the first thing that's very interesting. And if we put some numbers in, we can look at the typical discharge flow rates of both the fine and coarse particles, and we can estimate that the effective buoyancy of this mixture coming off the ship, the mixture of water and particles, is about 0.1 meters per second squared. And so the buoyancy flux is somewhere in this range. And then we pop that into the formula we just had, given the stratification of the water column. So if we inject the water down here somewhere, our mixture of particles and water down there, it'll travel maybe 200 meters before it knows about the stratification. If we put it right at the surface where it's very stratified, it won't actually travel very far before it's arrested by the stratification. So if we're trying to get this material to sink down through the water column to the seabed and sediment, we might want to inject it deeper in the water column below the thermocline, so it sees a much weaker stratification and the convection carries it further downwards. But of course, in the water column, there's actually ambient currents, and they're going to have a big impact on the dynamics of these flows. So we've done a series of additional experiments looking at what cross flows do to these currents. And here's an experiment where we have a tank. Instead of having water move along the tank, we actually just move the source providing the salt water. So here's a saltwater plume. We tow the source along the top of the tank, and we get a plume develop. And in this experiment, we change the color of the dye in the salty water. And what you can see is that very quickly, even though the source is moving, the water adjusts to the speed of the water in the plume adjusts to the speed of the water in the tank. And this boundary between the two colors of dye doesn't really move laterally along the tank. And here's a movie of the experiment. in the frame of this moving nozzle. So we've just processed the video and put it into this frame so we can see the plume as you'd imagine would happen if you're standing on the ship watching this plume spread away from the ship. And so it sinks down, there's a lot of turbulent entrainment, so it grows thicker and thicker as it sinks down through the water column. And what we want to do is understand the dynamics of that and then look at what happens if we put particles in that plume. Well, just to emphasize the fact that this is behaving as if the fluid is all moving with the fluid in the water column, we've carried out an even simpler experiment where we just release a cylinder of dense water and we let the cylinder of dense water sink through the tank. And what we do is we then use this false color, this is just an image processed picture of the dyed fluid, and we look at the horizontal average of the distribution of colors through the tank, and we plot a time series of that. So this is a time series of a horizontal average of each of these images. So it's just showing the cylinder of water sinking through the tank. And the shape of that flow actually looks very similar to the shape of the plume that we saw on the previous slide, just by doing a time average of this flow structure in the frame of the nozzle. And so the fluid we have here is sinking as if it's very similar to the flow that develops when we just have a lined cylinder. So each of these particles of fluid essentially is just moving vertically down through the water. And because of that, we can then develop a simple model to understand these dynamics. And particularly, we want to understand the dynamics, the trajectory of this fluid, and we can follow the center line of this fluid by, again, looking at the image processed light intensity of the time average. We can plot the distribution of intensity across this, and we see that these are all essentially Gaussian distributions, and we can then look at the center of that distribution to work out where the center of this plume is. And we can then compare that with a simple model where we assume that the horizontal speed is given by the current speed and the vertical speed is given by, just from dimensional analysis, it's the amount of buoyancy per unit length. So as this fluid comes out the nozzle, each of these parcels of fluid, there's a certain volume of fluid that comes out that then sinks at that depth. So by dimensional analysis, B over W, where W is the current speed, and then Z to the minus half gives you the speed of the vertical flow, and K is an empirical constant, which accounts for this turbulent mixing and dilution of the flow. And so we can get an expression for the trajectory, and if we plot that trajectory, it agrees very well with experimental data for a number of experiments. And so if we then start putting particles into these flows, we can start understanding the effect of particles. And what you see here is a snapshot of an experiment where we have very small particles and dyed fluid, and we can see that it all remains coherent and we get a convective flow. And here's an experiment where we have larger particles and dyed fluid, and you can see the particles now start separating from the fluid. And here's an experiment of that latter situation. You can see the fluid and the particles come out the nozzle, and the particles begin to separate from the fluid, and we get a fluid plume from that source fluid, and then we get the particles. And so we're able to track both of these to understand some of the environmental impact of this process. So what we can do is we can take that model we had just a minute ago, looking at the trajectory of the plume, the center line of the plume, and we can compare that with the trajectory of the fluid and also the trajectory of the particles. And what we'd expect is that when this vertical speed of the plume becomes comparable to the speed of the particles, the sedimentation speed of the particles, that the particles will start separating from this plume and the dynamics change. And so what we've done in this plot is we've plotted that theory for the shape of the trajectory, and the red line corresponds to an experiment with very small particles, and so they track that model trajectory very well. But as we make the particles larger and larger, what we see is they start falling down through the water column more and more quickly, because they're separating from the plume and they're actually sedimenting. We imagine they're sedimenting more quickly than this convective speed, because the convective speed decreases with depth. It goes like Z to the minus 1/2. And to test that, we can actually plot the ballistic trajectory. So here we're just plotting Z in the vertical and then a scaled horizontal distance, which is just the ratio of the fall speed and the current speed times the horizontal position. And if it's a ballistic trajectory, you'd expect that to be a straight line. And the small particles fall out faster than that because they're convecting, and while the convection speed's bigger than the fall speed, they'll fall quicker. But the large particles that separate and have a large fall speed actually fall out after they've reached a certain depth. They fall out by sedimenting more quickly than the convective speed. And so they follow this trajectory of the simple ballistic sedimentation. And so we now have a very simple way to understand how small and large particles move and whether they're convecting with the plume or moving individually. And we can look at the threshold value between the convection and the sedimentation just by looking at the experimental data that distinguishes where the fluid is and the particles are. So the gray cloud is the particles and the red is the fluid, just the dyed fluid we've injected. And if we look at that transition point where they begin to separate in space, there's a very good agreement with a scaling for where we'd expect that to occur. Well, the extra complication in deep sea mining is that if you're on this drill ship, initially I said that what you might want to do is inject the mixture in the water column somewhere below the surface. And so this introduces the fact that because the water's stratified in the ocean, the density of the water at the point where you inject that mixture might be different from the density of the water that you're using to make the suspension of particles. And so, for example, if you drew water from the surface and suspended the cuttings in that surface water, when you inject that from the nozzle, that water is going to be relatively less dense than the surrounding fluid. The bulk density of that water plus the particles could be heavier than the fluid, but the actual water will be less dense. But alternatively, you might source that water from deeper in the water column, in which case the water that you're injecting could be denser than the water around you where the nozzle is. And so there's sort of three different regimes that can occur. And there's a situation where both the water is dense and then the mixture of water plus particles is also dense. But as the flow evolves, we'd expect the particles to settle out. And so we'll get two sinking plumes, a water plume and a particle plume. We'd expect another situation where the water is less dense, but the mixture is initially heavy. So the mixture of fresh water plus particles is denser than the surrounding water. So it'll sink as a plume. But as this slows, the particles start settling out, the water will then separate and rise to the surface. And then you might imagine another situation where the water you inject, the mixture of the near surface water plus particles is actually less dense than the surrounding water, and that mixture rises through the water column, but eventually the particles settle out and they go a separate way. So there's sort of three regimes you can imagine in this density plot of particle load and salinity of the injected water. And I can just show some movies. So here's an experiment where we have a tank where we're injecting, the tank is full of salt water and we're injecting fresh red water and particles. And initially it's dense, and so it sinks down, but as you see, as it goes tens of centimeters from the source, the particles start separating from the water rises to the surface, and the particles carry on sinking. And this second example looks at a situation where the mixture is buoyant. Now the fresh water plus particles are buoyant, but as the mixture rises, the particles start falling out, and so we just get a rising plume, and then we have particles sedimenting from that rising plume of water. And both of these examples show that there's a potential that the particles get dispersed very widely over the whole depth of the water column, because the water density in this injected plume may be different from the density of the water in the background ocean. And so it may be that even if you inject deep in the water column, you end up dispersing particles over a very large distance. And we can sort of we've done systematic experiments tracking this. And what we find is that if we have a dense plume, dense water and dense particles sinking down, we can track how they move through space. And using that simple model we saw before, if we use the net buoyancy of both the particles and the saltiness, the experimental data shown in solid lines map on very nicely to the model prediction. We can look at the case where the water is fresh and the particles are heavy and the mixture is net dense initially. And in this case, we see the fluid trajectory initially falls but separates, and the particles, once the fluid's separated, the particles move along straight lines, and so they're really moving ballistically now. So these particles just sediment through the water column and the convective flow stops. And then finally, we can see the situation where the mixture is buoyant initially, but the particles sediment. And once the particles are sedimented, the rise speed increases because it's lost this heavy load of particles. And so with very large particles, we find the height increases quite quickly. But with smaller particles, the particles stay in suspension. They don't sediment as quickly. And so the rise speed of this plume is slower. And again, there's a mapping from very small to very large particles. So if we're interested in the implications of this for deep sea mining, what we found is that there's a sedimentation, well, we know there's a sedimentation speed, and we look at the typical size distribution of particles in deep sea mining, which are of order 100 microns up to a millimeter or so. They have fall speeds 10 to the -3, 10 to the -2 meters a second. And so if we compare that to the current speed, what we find is there's an initial phase where we get a plume flow, a convective flow, which carries the particles down quickly in the convective flow, but then the sedimentation occurs and we move to a pure ballistic sedimentation regime. And so we can estimate how far these particles are transported from the mining site before they land on the seafloor to understand the impact of this. And looking at these numbers, we find there's a range of perhaps up to 100 kilometers from the ship where they'll settle on the seafloor. And so the zonal impact of this sedimentation from the tailings may be up to 100 kilometers. That I said at the beginning, the area of the deposits might be of order 1 million kilometers squared. And so there's a zone around that, which may be 100,000 kilometers squared, where some of this sedimentation may occur. And so you may be wondering, well, how can we reduce that? What have we learned from this? This discussion about the complexity of the sedimentation. Well, the thing we've learned is that if we actually sourced the water from the seabed, where the water is the densest, and then we injected the particles with the water down near the seabed, then the flow would be heavy and it would spread out along the seabed, and so we'd suppress a lot of this convective motion. And so the recommendation would be that, although it would be more expensive and difficult, we'd like to dispose of the particles near the seafloor, and that would lead to gravity currents on the seafloor, which would travel much smaller distances and impact a much smaller zone around the mining site. And just to finish off, I just wanted to summarize, we've seen some very simple models here that allow us to understand this balance between sedimentation and convection with sort of important implications for deep sea mining. But there's also important implications of this physics for volcanic eruptions. And here we see Mount Pagan that was erupting, and we see sedimentation of ash over the land from this plume rising in the wind. And that's very similar to our experimental model, where we just superposed the landscape onto the experimental tank. And we're presently looking at some of those dynamics. So at that point, I'd be very happy to take any questions, and hope this has shown you an interesting application of flow, which has potentially important implications for a number of natural processes and geophysical processes.
Thank you. Thank you very much, Andy. Or sorry, one person asked about the Reynolds number of the jet in the experiments, and someone else asked about the.
Yeah, I can see those. Yeah, so the jet Reynolds numbers in the experiment. So we're looking at many thousands of the Reynolds numbers are thousands or bigger. These are quite big scale experiments. So our tank is meters long, and so these are highly turbulent flows. And then Bruce, I think the concentration of particles released in the ship will be in a few percent, just in order that the flow won't jam up and clog. So there may be some particle interactions initially, but I think it gets very diluted as these flows sediment through the water column, and so the concentrations are much smaller. So I think there may be, I'm not sure there will be hindered settling. When we've analysed the descent speed of the particles, it follows those ballistic trajectories with the expected fall speed quite accurately to leading order. But there may be some effects. There's obviously some convective effects in the more concentrated region near the source, but the overall buoyancy of the plume is controlling the mixing, and the whole system is a big vortex as it sinks through the water column. Are Richards type diffusion observed? So there is some spreading of the particle cloud. The third question, there is some spreading of the particle cloud as it sediments through the water column, but some of that in our experiments is due to the fact that our particle size isn't exactly unique. When we buy the different grit we get, there is a small size range, and that can cause a slight spread in the fall speed. So I think that's one of the reasons why we're seeing the sediment cloud gradually spread out. And Oliver, how do you work out what is least damaging to the ecosystem? So that's That's a very difficult question. And so I'm not an expert on the ecosystem, but I think what we're trying to do is understand how do we minimize the region beyond where the mining might occur, on which particles sediment. And I think these experiments and these conclusions suggest, there is a strategy to minimize the transport distance of the particles, to keep it as close as possible to the mining site. Clearly in the mining site, the seabed is being very much disturbed, but there's a lot of regulation and policy to come in, but this sort of work hopefully can inform some of that.